Okay, so in this section we're going to review the paging memory management mechanism, and although we've simplified this to a fairly considerable extent, this paging mechanism is the basis of memory management in contemporary operating systems. So this is how it's done in things like your phone, in terms of tablets, and in terms of desktop PCs. So we'll go and work our way through this content, and hopefully by the time we're finished you'll have a reasonable understanding of why paging is a solution to the problems of memory management that we've just identified. So we can see that contiguous allocation of physical address space to processes is not a wonderful idea. It won't work very well. So with that in mind, let's skip on to the next slide. We will note that the main benefit of paging is that it reduces the impact of allocation and fragmentation. Okay, so really what we're looking for is the efficient use of memory, and paging allows us to do that. Now the way that it does this is that it allows for the allocation of the logical address space into the physical memory to be non-contiguous. So although the logical address space will essentially be contiguous from the perspective of the user process, in reality its actual allocation in physical memory will be non-contiguous. So that's the big innovation, if you like, in terms of paging. So there are really a kind of couple of fundamental ideas that we need to take on board. The first one is that physical memory is broken into chunks or blocks, which are known as frames, and that logical memory is broken into blocks, which are called pages. Now the important thing is that pages and frames are the same size, and they're always a power of 2, so they might be 512 bytes, 1024 bytes, 4096. So I think that the standard for desktop PCs at the present time is 4K, 4 kilobytes, 4096 bytes. Now by keeping these numbers as powers of 2, this allows us to play arithmetical tricks when we come to do the mapping of logical to physical addresses. And that's really important because one of the things that the memory management unit has to do is to operate without slowing down the system in any way. So we want to be able to do this in an efficient way. So the next slide shows us the kind of general arrangement. As before, we have our components. So for example, we have our CPU, we have our physical memory, and then we have the memory management unit, which contains all of the functionality that we can see here in the middle of the page. So we can see that there's a data structure which is called the page table. So I'll just change that to highlighter. So this is the so this is the page table here, and then you have your logical addresses which are translated into physical addresses just as before. So what we can see is that each logical address has two components to it. It has a page component and then a value which is referred to here as D, but you might think as the offset or the count from the beginning of a particular page or a particular frame. So that'll become a little bit more clearer later on, and again it relies on a little bit of arithmetical trickery in terms of the binary numbering system. So I think the easiest way to deal with this is to skip to a graph, a picture, and then talk about the way that it's done, way that the paging thing is done in general. So in the slide on slide 38, or in the picture on slide 38, we can see that we have a process whose logical address space consists of page 0, 1, 2 and 3. And what we can observe about that logical address space is that it is contiguous. Okay, so from the perspective of the user process, it exists as one chunk of logical memory. But what we can also see is that in reality, the pages of the logical address space, when they are actually allocated into their corresponding frames in main memory, well, we can see that the allocation of the pages into available frames is not contiguous. So the mapping between pages and frames is obtained by this data structure here, which is internal to the memory management unit, and we can see that pages are mapped to frames. So you can see I'm drawing a tiny wee arrow and I'm showing you that page 0 is mapped to frame 1, like so. You can see that page 1 is mapped to frame 4, like so, and page 2 is mapped to frame 3, like so, and then finally page 3 is mapped, that's not quite right, page 3 is mapped to frame 7. Okay, so page 3 is mapped down here. And what we can see is that the pages, when they're stored in main memory, they are non-contiguous. Okay, so what that means is that if we need to store 4 pages belonging to a process, then we don't need to find a chunk of contiguous memory which is 4 pages in size. All we need to find is 4 frames anywhere in physical memory that are available, that are free for us to store pages into. Okay, so this is the general structure of how it works. The translation, if you like, is taken care of in this central structure here, which is the page table. Okay, so it's the page table that we're particularly interested in, but the other big innovation is the idea that the actual storage of the process's pages in physical memory, that is non-contiguous. Okay, so the next slide, slide 39, has an elaboration of the diagram that we've just looked at. So you can see that, as before, we have a page table. You can see that we also have a logical address space for a particular process, and then you can see that we have a physical memory. Now we're told in the caption that the size of this physical memory is 32 bytes. Okay, so obviously this is wholly unrealistic, but that's okay, it's only for illustration. And then what we're also told is that each of the frames inside the physical memory is 4 bytes in size. So obviously if each frame is 4 bytes in size, then so must each of the pages. They have to be 4 bytes in size. The other thing that we're told as well is that instead of showing you real machine code instructions and real program data, what we're going to do is we're going to assume that letters of the alphabet, A, B, C, D, and so on, that they represent the program's code and the program's data. So another observation as well is that each the logical address space of a process can be represented by its logical addresses. So you can see we saw those before, so you can see that there are 16 logical addresses in this program here, and that there are 4 pages for 4 logical addresses. So logical address 0 through to 3 is stored in page 0. Logical addresses 4 through to 7 are stored in page 1. Logical address 8 is stored in logical address 8 through to 11 is stored in page 2, and logical address 12 through to 15 is stored in page 3. The page table shows us that page 0 is stored in frame 5, and in fact if we look at page 0, which is here, you can see that it has A, B, C and D as content, and then when we go and look at frame 5, we can see that frame 5 contains A, B, C and D. What you'll also note as well is that the physical memory, right, is broken up into not just frames, which we can see here, but it also has an address range which starts at 0 and goes all the way to 31, which is down here. So another way of putting that is that logical address 0 is stored at physical address 20. Logical address 1 is stored at 21. Logical address 2 is stored at 22. And logical address 3 is stored at 23, as well as being stored in frame 5. We can see also that page 1 is stored in frame 6. So here's frame 6 down here, and you can see that its starting address is 24, and you can see that when you look at page 1, its contents are E, F, G and H, and when you look at frame 6, you can see that its contents are E, F, G and H. And then when we look at page 2, you can see that it is stored in frame 1. So you can see that the physical starting address is 4 for frame 1, and you can see that the contents of page 2 are I, J, K and L, and there's the corresponding content over here, I, J, K and L. And then finally we have page 3 stored in frame 2, which we can see here, and then you can see that its starting address is 8. So for example, if we were looking at the machine code instruction M, okay, so there's M, its logical address is 12, and its physical address is 8. If we were looking at the machine code instruction N, well, its logical address is 13 and its physical address is 9, like so. So we have to figure out a way of mapping the logical addresses to the correct physical addresses. But that mapping is slightly more complicated because the frames in physical memory are not contiguous. They are stored elsewhere. They're stored in whatever frames are available. And we also have to do it in such a way that the translation mechanism, the mechanism of the page table, not only converts pages into frames, but also converts logical addresses into physical addresses. So this is done by a mapping which is discussed on slide 43. So I'm skipping past a couple of slides for the sake of convenience, but what I'm trying to do all the time is to keep this diagram in mind when we are thinking about slide 43.